Have you ever wondered how computer experts and analysts measure how fast different algorithms are? That's where big O notation and time complexity come in. Today, let's take 5 minutes to get an introduction to what time complexity and big O notation even is. Starting out, what is big O notation? Big O notation is a fancy math way of saying how much time or memory an algorithm needs based on how big the problem is. In simple words, it tells us if an algorithm gets slower or it needs more memory as the problem gets bigger. Now let's talk about time complexity. Time complexity is like a clock that shows us how long an algorithm takes to solve a problem, depending on how big the problem is. Time complexity helps us see how the speed changes depending on a problem's size. Now, let's go through the most common time complexities and give examples to help you understand it. We'll start from fastest to slowest. O of 1, constant time. Algorithms with constant time complexity execute in the same amount of time, regardless of the input size. This is like an algorithm that's always lightning fast, no matter how big the problem is. For example, it could quickly grab the first item in a list or do simple math. No matter how big your list is, the time complexity will always be the same because it's grabbing the first item in the list. O log of n. Logarithmic time. Algorithms with logarithmic time complexity have a runtime that grows logarithmically as the input size increases. This means an algorithm gets a bit slower as the problem gets bigger, but not by much. Think of searching a phone book. It's faster because you split it in half each time. Examples include binary search on a sorted array or certain divide and conquer algorithms. Quick break. If you need help on your software testing journey, check out my website, thetestinglead.com. Now, back to the video. Linear time. Algorithms with linear time complexity have a runtime that grows linearly with the input size. Here, the time it takes for an algorithm to solve a problem increases in a straight line with the size of the problem. It's like checking each item in a list one by one. Examples include iterating through an array or performing a simple search. Big O of n squared, quadratic time. Algorithms with quadratic time complexity have a runtime that grows quadratically with the input size. This is when an algorithm starts to slow down a lot as the problem gets bigger. Imagine going through a list, and for each item, you have to go through the list again. It's much slower. Examples include nested loops, where each loop iterates over the input. Big O of 2 raised to the n. Exponential time. Algorithms with exponential time complexity have a runtime that grows exponentially with the input size. This is the slowest. An algorithm's time or memory needs grow super fast as the problem gets bigger. It's like a snowball rolling downhill, getting bigger and bigger really quickly. Examples include certain recursive algorithms that exhibit exponential growth. Now, you might be thinking, but why does it matter if something takes 1 second versus 2 or 3 seconds? What's the big problem? If you're running your program or code once, then yeah, you probably won't see in real time the time difference. But now imagine your piece of code is being ran thousands or millions of times daily. That 1 second or 5-second difference grows exponentially depending on your time complexity. So in short, we've introduced big O notation and time complexity within about 5 minutes. So the next time that you're stuck with an algorithm, you can think about the most efficient and best time complexity for your project. If this video helped you at all, please like, share, and subscribe. And most importantly, don't forget this, learn something new today.